Section 10-2 is on distance, displacement, velocity, and acceleration for linear motion. The objective of this section is given velocity or acceleration for an object in linear motion, find the displacement and distance. And if you go back all the way actually to chapter 1, we were first introduced to this idea when we were working with definite integrals. We saw that if we started out with acceleration, that the antiderivative of that, or the definite integral of that, gave us velocity. And the definite integral of velocity gave us our displacement, or vice versa. If you started with displacement, the derivative of displacement gave us velocity, and the derivative of velocity gave us acceleration. So those are the types of problems we're going to see in this section. Let's start out with displacement and distance, just to remind you of the difference between the two. In fact, let me draw a sketch to remind you of that. Let's say that we have a point A as our starting point and a point B as our ending point. Now we're talking about linear motion, so it's just in a straight line between these two. But let's say to move from point A to point B that I actually move to the left first, and then I turn around and I head to the right for a while, and then I get to some point and I turn around and I head back and end up at point B. So that path that I took there, the length of that path is the distance. On the other hand, if I were to just measure that path that goes from point A to point B, measure the length of that path, that is our displacement. So that's the difference between the two here. So again, from what we learned way back in chapter 1, we learned that if we find the definite integral of velocity, it turns out we end up with our displacement. So the definite integral from point A to point B of our velocity function gives us displacement. On the other hand, if we find the definite integral of the absolute value of our velocity from A to B, turns out we end up with our distance. And the reason why it's the absolute value is you can see there in our sketch that we drew over to the right. When we head in different directions, we have a change in sign. In fact, when we head to the left, we have a negative sign that we'd use to indicate that that part of the path, and when we head to the right, we use a positive value. So the absolute value there gets rid of those signs for us and basically takes into account the entire path as opposed to just the direct path from point A to point B. And kind of coupled with that is the relationship between speed and velocity. Speed and velocity are related, but speed is the absolute value of velocity. It's your velocity without direction. The direction of velocity is the positive or negative that comes along with it. In fact, up above there, as you can see when we were talking about distance, distance was the definite integral from A to B of absolute value of velocity. Turns out that's just speed. So your definite integral of speed gives you distance, and your definite integral of velocity gives you displacement. Now if it turns out your function has a positive velocity, which speed is also always positive, turns out then that the integral of velocity would be both displacement and distance. And in some cases that turns out to be the case. Let's look at a couple of examples. Look at example 1 on page 502. It says a moving object has a velocity v of t is equal to t squared minus 7t plus 10. And it says this is in feet per second. And it says it's in the time interval from 1 to 4. So we're going from 1 to 4. All right. Part A says to find the time intervals in which the velocity is positive and the subintervals in which the velocity is negative. So basically what I need to do is find out where velocity is 0, and I know that at a 0 it's going to be changing, or potentially changing, from positive to negative on one side or the other. So let's find out where our velocity function is equal to 0. And there's actually several ways you could solve this. You could graph this and find out where the zeros are at. You could use, it's a quadratic equation, so you could use your quadratic formula. This actually factors nicely, so I'm just going to do it that way. T minus 2 and T minus 5, it looks like, right? It's two factors. And so that means that T is equal to 2 or 5 are the two zeros for this function. And that was not the question, remember. The question was, where is the velocity positive and where is it negative? We found out where it's 0. But now that I know a little bit more about this function, I know it's a quadratic function, so I have the general shape in mind of what it looks like, but I also found out that at 2 and at 5, this thing crosses the x-axis. So this has a graph that looks something about like this, we'll say. And so knowing that, I can see where my velocity is positive and where it's negative. However, remember, they only want us to consider the interval from, let's say this is 1 to about right here would be 4. So I only have to worry about this interval from 1 to 4. So that means that the velocity function starts out positive from 1 to 2, and then it's negative from 2 to 4. So let's go ahead and write that down, that v of t is greater than 0 on the interval from 1 to 2, and it's not including 2 because at 2 we're equal to 0, not greater than 0. And v of t turns out to be less than 0 on the interval from 2 to 4. And again, not including the 2 because, of course, at 2 we were equal to 0. All right, so that's part A. Part B now says, find the distance the object travels in each of these subintervals. So we're going to take each of these subintervals and find out how far we've traveled in each of those. So the interval from 1 to 2 we'll start out with. We'll integrate our velocity function. The integral of velocity gives us our displacement, which in this case, since velocity is greater than 0 on this interval, it's also the same as our distance. Again, anytime you're working with a positive velocity, that means that it's going to be the same as the integral of the absolute value of itself. And so you get distance as well. And we'll punch that in our calculator in a second to find out its value. For the second subinterval, we want to integrate from 2 to 4, but velocity is negative there. So I need to take the opposite of velocity so that I'm integrating a positive value. And thus I'll be finding my distance on that subinterval. All right, so let's punch those into our calculator. And actually I put in y1 as my function there already. So let's just use numerical integration. And we're going to integrate y1. Our variable is x, and we're going to integrate from 1 to 2. And we get 1.83 repeating for this first one. 1.833, or that's actually 1 in 5/6. That's in feet. And let's do the same thing for the second integral here, but it's going to be from 2 to 4, and it's the opposite of my velocity. So I want to change this and add in a negative. And we're going to go from 2 to 4. And we get 3 and 3.3 repeating, so that's 3 and a third. And again, this is in feet. They told us that our units here were, for velocity, were in feet per second, so this is in feet. All right, so that is part B. Let's take a look at part C. It says in part C now to use a single integral to find the displacement in the time interval from 1 to 4, and another single integral to find the distance traveled in this interval. All right, so now we want to do this with a single integral. We did it here in part B with 2 integrals. Let's see if we can do this with just 1. All right, this is what we saw in the previous slide here actually, is that to calculate displacement, that's just the integral from 1 to 4 of your velocity function. And we'll punch that into our calculator in a second. We'll get that value. And we said that the distance is equal to the integral from 1 to 4 of the absolute value of velocity. And actually, I have an absolute value function on my calculator, so I can even do that on my calculator. So let's try that out. Let's just clear those out of there and go back and change this first entry. It's the integral of my velocity function from 1 to 4 is what I want to change. And we get a negative 1.5. And again, that's in feet. And let's check out the second calculation here, which this one is our distance, but I've got to make this the absolute value. So if you insert the absolute value function in there and integrate again from 1 to 4, it'll take a few more seconds to calculate that value, but it's 5.167 it looks like. 5.167, or actually that's 5 1/6 feet is what we end up with there. Again, you could use fundamental theorem to evaluate part B. Part C, you could do the first one with fundamental theorem, but the second one there, because it's got absolute value, you'd have to break it down into two separate integrals, just like we did back in part B, in order to use fundamental theorem on this. But you could certainly do it that way. All right, look at part D now. It says show how you can find the answers to part C from the answers to parts A and B. So we'll use actually mostly our answer from part B, I guess. Part A was just simply finding where it was positive and negative. But to find your displacement, and using the two values we came up with in part B we found out that from 1 to 2 we had a distance of 1.56, or excuse me, 1 5/6 feet, and from 2 to 4 it went 3 1/3 feet. So if I take the 1 5/6 feet, that is where our velocity was positive. And for displacement, I want to keep the sign of velocity. So from 2 to 4, we integrated the opposite of velocity. So if I add on the opposite of that distance that we found, add negative 3 1/3. If you punch that in your calculator, you'll get a negative 1.5 feet. That's the value we got up above there in part C. And you can do something similar there for distance. If we take our distance, take the 1 5/6 like we did before. That's the interval that our velocity was positive on. And then from 2 to 4, our velocity is negative. So I just add on the 3 1/3. Don't change its sign. I want it to be positive. The distance is always going to give me a positive result. If we add those up, we end up with 5 1/6 feet. That's the value that we got up above there. All right, so let's take a look at another example. Look at example 2 on page 504. Example 2 says a car accelerates for 24 seconds. Its acceleration in miles per hour per second. Notice the units there, by the way. There's hours and seconds in those units. Be careful with those. Is measured every 3 seconds and listed in the table below. Okay, so they give you time, which is measured in seconds. They give you acceleration, which is measured in miles per hour per second. So for part A, it says to plot the graph of acceleration versus time. So let's just take that data and put it into our calculator and do a scatter plot of this information. In fact, I have that already punched into the list editor there. I've got my data in list 1 for my time, and in list 2 is the acceleration. All right, so let's just have it do a stat plot of this thing. Let me get rid of this function here. I don't need that anymore. And we'll do a stat plot. Turn that first one on. I'm going to go ahead and do a connected scatter plot there. We'll use list 1 and list 2, and I'll use this square here as my mark just so I can see each of those points. Let's just set up our window. Now the x values are the times that they gave you there. So those go from 0 to 24, but I'm going to actually go back a little bit. I'm going to go back from -3 to 27, a little bit to the right of those values, just so it's easier to see the first and last values. And I'll set a scale of 3, since they're 3 seconds apart. And then for my accelerations, it looks like the largest acceleration was 2.2. The smallest was a -1.4. So let's go from -2.5 to 2.5, and we'll set a scale there of 0.5, and we'll graph that. There is our sketch of the acceleration. In fact, let's grab a picture of that. Because that right there is part A of their question. All right, so part A is done. Was the graph of this thing. So let me move that over just a little bit. All right, for part B now. Part B says at time t equals 0, the car was going 20 miles per hour. Predict its velocity at each 3-second instant, all the way from 0 through 24. All right, so they gave us an initial velocity of 20 miles per hour, and the question is, what's the velocity at 3, and then at 6, and then at 9, and so forth? Well, if you recall from our fundamental theorem of calculus, we can use that to help us come up with those values. In fact, the fundamental theorem of calculus if I integrate my velocity or my acceleration function, let's say from 0 to 3, when I integrate this, this actually tells me a change in velocity. It's actually my antiderivative of acceleration, which is velocity at my upper bound, 3, minus my antiderivative velocity at my lower bound, 0. So it's telling me a change in velocity over that interval. It tells me how much it changed by. And if I know I started out at 20 miles per hour when time is 0, and this tells me how much I change by in that interval, I can then figure out what's happening at 3 and then at 6 and so forth. In fact, I can solve for v of 3 here. Just move v of 0 to the other side. So I have v of 0 plus that integral from 0 to 3 of acceleration. In fact, they told you that your velocity at time 0 was 20, so we know that. And integrating my acceleration function from 0 to 3 is basically the same as coming over here to this graph and finding the area of this region. Now that's, of course, approximating it using a trapezoid, but we can come up with a pretty good approximation for what the integral from 0 to 3 is equal to. In fact, they told us that the when time is equal to 0, this acceleration is 1.3. Over here it's 1.7 when time is 3. And this is a 3-second interval right here. So I know the dimensions of my trapezoid, so I can actually write those down. We get 1/2, and then it's the sum of the two bases there, the 1.3 and the 1.7, times the height, or the distance between those two bases, is 3. In fact, what is that? 1.3 and 1.7 is 3 times 3 is 9. Half of that's 4.5. So you get 24.5 is the velocity at 3. Now for the units, again, you got to be careful with these. Our x-axis is measured in seconds. It's time measured in seconds. Our y-axis is our acceleration, and that was in miles per hour per second is the units that we have there. So when I go and find the definite integral here, we're finding the product of my x's and y's. We multiply those two together, multiply the units for x and y together. We end up with seconds times miles per hour per second. And you'll see that the seconds cancel out, and those leave us then with just miles per hour. So those are nice units that we end up with in this part of the problem. We get 24.5 miles per hour is the velocity at 3 seconds. And then I can continue doing this to find out the velocity at 6 and then 9 and 12 and so forth, all the way up to 24 seconds. But you can see basically this is using a trapezoidal method to approximate this definite integral. And so it's basically running our trapezoid program, and even better yet, I've got a program that I'll give you that I'm going to run right now that is kind of more appropriate for what we're doing in this section. And the first thing you have to have is in your list editor, you've got to have your x and y, your time and acceleration in this case, already put in. And then you can run the program. It's ACVALDIS, I guess you might say, but it's just the abbreviation for acceleration, AC, velocity, VEL, and displacement, DIS. So that's the name that I have there for it. But if we run this, the first thing it's going to ask us for is what do we have in list 2? List 1, it says at the top, list 1 is equal to time, so you have to have time in there. List 2, it could either be acceleration or velocity. So it's asking you what have you put into list 2. We put acceleration in there, so I'll just choose option number 1 there. And now let's it brings us to the next question, which is what is your initial velocity? They told us that was 20. And it doesn't do any, it doesn't display any information out here for you. It just tells you where it dumped the information. Basically, list 3 is your velocity, list 4 is your displacement. So let's go back to our list editor. And you can see now in list 3, I have some data there. And that data is the velocity. In fact, you can see that when time is 0, that your velocity is 20. Well, that's because that's what we put into the program there. It asks us what our initial velocity was, so that's not a surprise. The next value, though, when time is equal to 3 seconds, our velocity is 24.5. Well, that's what we just calculated over here on the right. So our calculation is correct there in comparison to what our program's giving us. And if we run through these numbers here, you can see we continue to accelerate here. Our velocity is getting greater and greater. That corresponds to our positive acceleration, by the way. And accelerates all the way up to 44.9. And all of a sudden, when our acceleration becomes negative, we start decreasing here in velocity, and we end up with 38.75. So there is the velocity at each 3-second interval. Okay, so our trapezoidal method basically gives us those calculations. All right, look at part C now. Part C says to plot the graph of velocity versus time. So now to graph velocity versus time, I'm looking at in list 3 here, my velocity, and my time is in list 1. So I can just use this data to graph that function that they want. So let's go back to our stat plot. We'll just change it slightly. And instead of using list 1 and list 2, we're going to use list 1 and list 3 is the velocity. And we'll change our window here. My x's can stay the same because we're still looking at the same time interval. But for my y values, again, the largest velocity that I saw there was 44.9. So I'm going to go from 0 to 50. Our velocity was always positive in this case. And we'll set a scale of, we'll do 5. Again, you can modify your window there slightly if you prefer a slightly different window. That's fine, but just get a nice sketch of your velocity function. There we go. In fact, let me grab another picture of that so we can use that to answer the next part. All right. So this was part C of this question, was to sketch our velocity function. Now for part D, D says approximately how far did the car go in the 24-second interval? So again, using the same logic that we did in the previous part of this question, we can come up with how far the car went. So let me move this back up. The idea is based on the Funwell theorem, and what the Funwell theorem tells me is that if I integrate my velocity function, let's say from 0 to 3 again, that's equal to my displacement function, I'll call that d, evaluated at the upper bound, minus my displacement function, at the lower bound is not 3, it's 0. Okay, the antiderivative of velocity gives me my displacement there, so it's the difference in displacement. So again, I can use the same method here to find out my displacement at 3 is going to be equal to my initial displacement plus my change in my velocity function, or I should say the area under my velocity function from 0 to 3. And so I can go through and find this much the same way that we just did the previous problem. In fact, it's already got the data dumped into list 4, if you recall. It said that it put the displacement in list 4. The only thing I got to watch out for are the units here again. Again, my x-axis is my time, and that's measured in seconds. But my y-axis is my velocity, and that's measured in miles per hour. Okay, so when I go to grab these values, remember it's the product of these two, and it's going to tell me my displacement, but it's going to be some weird units here. We're going to change those in just a second, but let's, this is part D. Let's find out what our calculator gave us for our displacement at 24 seconds. So if we go over to list 4. So initially our displacement is 0. Now again, if it's not 0, then you can just add some constant to each of these values in this list. But otherwise, at 3 seconds, it's 66.75 and so forth. All the way up to 24 seconds, it's 886.125. 886.125. And I'm going to go ahead and write that down, but I'm going to put the units here along with it, and this is why units are critical for any type of problem. But my x units are in seconds, my y units are in miles per hour. So we get some weird units here, miles, seconds per hour. I don't know how you want to read that off, but that's not usually how we measure a displacement. So I need to convert this from these weird units to just miles is what I want to do. And we can do that by multiplying by a clever form of 1, remember. I need to get rid of the hours that are in the denominator, so I'll put hours in the numerator here. And I need to get rid of seconds, which are actually in the numerator, so I'll put them in the denominator over here. And I just need a conversion from hours to seconds then. I know that 1 hour is equal to 3,600 seconds. Now because the numerator, 1 hour, is equal to the denominator, 3,600 seconds, I'm multiplying by 1. I'm not changing the problem. But I will get rid of these weird units here. The hours here will cancel out, the seconds here will cancel out, and we'll be left with just miles. So if I take this answer and divide it by 3,600, then that's the distance I've gone in miles, and that's going to be definitely more useful for me. In fact, I'm going to just take the entire list. If I take list 4 and divide it by 3,600, in fact, I'll just dump that right back into list 4. Sometimes that's makes some more sense to just simply change the whole list. And oops, let's go back to list 4, and we'll run down to 24 seconds. 24 seconds, we went 0.246 miles. So this is equal to 0.246 miles. Definitely make sure you do the conversion there, get it into units that make more sense for the problem. That's the only thing you got to watch out for, is that this program's not going to take that into account. It's not going to ask you for the units. You've got to recognize that.